So today I will be talking about multimodality. And what multimodality is about is basically if you have multiple modalities and not just, for instance, for computer vision, we have object detection, which is technically one modality. You have the image input and then bounding box output or image classification. This is like single modality. If you have multiple modalities, like image to text, text to audio, and other things, your model becomes multimodal model. And today I will be specifically focusing about open multimodal models in the sense that when I say open, it's not altogether open source. What makes a model open source is the fact that this model can be used commercially. And so it's not only released openly, the weights aren't just there, but it can also be used for commercial purposes. So licenses like Apache 2.0 or MIT are completely open source licenses, for instance. But some models might be just open and not open source. So today I will talk about not only open source, but also open models. So I will be specifically focusing on multimodal vision because it's what I'm working on at Hugging Face. And there is three things. First one is vision language models. The second one also falls into vision language models, but when I say vision language model, it is actually a model that can have image and text or image, video, and text input and text output. And multimodal retrieval is when you have image query and text query, and you can do image to text search or text to image search. And for zero shot vision, it is zero shot. Also, it's called open set or open vocabulary. These terms, I think, like initially I was super confused, but these terms are used interchangeably when we are talking about zero shot models. And this is basically open vocabulary, object detection, zero shot object detection, um, zero shot image classification, and so on are falling under zero shot vision. But most of this talk will be focusing on vision language models because it's the hot topic these days. But I will be briefly going through zero shot vision. So the open alternatives for these tasks. So basically, there is the most famous multimodal vision model, I think, is GPT-4o. It's not only taking image as well, but it used to take image and text. There was GPT-4v. Or there are other alternatives that can take image and are closed source, but there is also open alternatives like QN2VL, Molmo, Pixtral, Llama 3.2 Vision, Lava, Polygemma. And then there is multimodal retrieval models like ColPoly, DAC, MCDAC, ColQN, ColFloor. And there is zero-shot vision models, like CLIP is the most famous example, SIGLIP, Grounding Dino, and so on. And why does open source matter? People are asking why should we rather be using open source. Firstly, you can just take these models and deploy them locally, which means that you can, for instance, deploy them for a browser and then just guarantee complete privacy of your users. And you can customize these models according to your use case. You can improve them, and you actually know what is going in the background. And also, you can quantize or distill a given model. And then you do not have any model changes in the backend for a given API that you're using. So basically, for closed models, you have model changes in the background without you knowing how it changes. And then, like if you're using a vision language model, your prompt might change, your system prompt or whatever. But since you will be owning the model itself, there is no such thing as model changes when you have your own model. And some common use cases are like, for instance, for document AI, there is multimodal RAG, which is about document retrieval. You can just query, you have a knowledge base, and then you can query, and then you can pass the output to an LLM and do multimodal RAG. You can have image understanding, like visual question answering, image captioning, and so on. For zero-shot vision, the zero-shot image classification models can be used for image search in a given gallery, like in your phones and so on. And you can also do distillation, as in, for instance, if you're going to do object detection and you do not have any labels, you can use a larger model, like open set object detector, and distill the labels of that to a given set, and check them out, see if the bounding boxes make sense, and then just come up with your first model instead of paying for data labeling. Which is actually like, then you can do self-training as well, in the sense that you can take that model and the student model, and then distill that model, keep labeling more model data, and then do continuous training on the synthetic data, which is a very successful training recipe these days. So the first multimodal model is the father of multimodal models, in my opinion. It is CLIP. So basically, CLIP is the first, in my opinion, first successful model to connect modalities. Back in the day, there were very few models anyway, but CLIP is still heavily used. It is basically like you have this dual encoder setup where you have this image encoder and then text encoder. This text encoder is taking in open set of labels and then encodes them, and then image encoder encodes images, and then they have this function that is image embedding multiplied by the transpose of text embedding plus the bias to be maximized. So this is basically the similarity function, and it is to be maximized for the images and texts that are the most similar. And then you need to minimize the rest of them. So if I can show this. So these ones should be the maximum, and then the rest of them, especially the least similar ones, should be the minimum. And this is what CLIP is doing. And during the inference, you get bunch of similarity scores as well, which I'm going to show. So SIGLIP is the most powerful image encoder text encoder model. It's just like CLIP, but with sigmoid activation in the end. And the good thing is, this is also open source, and people are training vision language models based on it, which I'm going to show later. But this model is a bit different. So basically with CLIP, in the end, the output probabilities are like adding up to 1, but in here it doesn't. So people are a bit perplexed when they see the output of SIGLIP. But I feel like it's better because like the best output is more amplified, and because of it, you get better top K accuracies when you are inferring with SIGLIP. And the cool thing is, like, for instance, you input an image and you input some candidate labels, like open-ended labels, like bee on a flower, bee in a hive, bee in the sky, and at the end you just get these similarity scores. And you can just do zero-shot image classification with this, or you can use the embeddings of this model. But yeah, like I'm going to show later how it can be used to train vision language models, but this is all you need to know for now. And for OWLWidth, which is a zero-shot object detection model, basically, this is just like SIGLIP. You input some labels and you input an image, but in the end, you get the bounding boxes of those open-ended labels in that image. In here, there is a video, but in that image, and it is essentially how open-ended zero-shot object detection works. So basically, this is very similar to clip architecture, actually, but you are trying to have this contrastive training of matching the texts to the best bounding boxes. It is just trained like clip or siglip. Before moving on to open vocabulary segmentation, we need to go through mask generation, which is the most famous task of this year. So you have this image, and then you can input either a point on the image, on the object that you would like to segment, or you can just put a bounding box around it, and it will generate the segmentation mask over this object of interest. So in this case, I'm drawing a bounding box on the B, and it segments the B. It is not, so basically the most famous model is segment anything model. I'm sure everyone knows it by now. It was released by Meta. This model is essentially not returning any semantically meaningful. I mean, it returns outputs that are somewhat semantically meaningful, but they are not. It doesn't return any class info or whatever, or any text, because it cannot accept text prompt. They only released the segmented model with bounding box or point prompt, so you only get the mask. So how it works is that you have an image encoder and then you have a prompt encoder. In this case, this text part is discarded, essentially. You can either get points or box prompt, and you get an image, and then you have a mask decoder which decodes these encoded inputs to segmentation masks. And they also released the second version of segmenting model this year, which solves another problem called masklet prediction. And masklet is essentially this segmentation mask that is propagated over time in a given video. So it's basically tracking the position of those of a given object that is segmented over the video. And they have added the memory module to do so, which is a bit complex, so I will not go through the details of this. But basically, this model is great because it can predict the segment, like it can do tracking very well without you passing the frames to the model and then using something like byte track to track a given object of interest. By the way, are we going to take questions at the end? I'm a bit fast, I'm sorry, but I have a lot of things to mention. Are we going to take the questions at the end of the video, or?
Yeah, I thought that it's best if we do that. Yeah.
Okay, so this is how it looks like. It is tracking on its own, and I think it's just amazing segment anything model too. And the good thing is you can actually combine these open set object detection models with the mask generation models, which was the point of my graduate school thesis as well. You can combine a model like OWL with a model like segment anything, basically get like input text prompt of and the image prompt. Like for instance, in this case, I'm prompting cat, and I pass this image to firstly OWL, and get the let's remember how owl looked like. Basically, get the text queries and their probabilities, and then pass these bounding boxes and their probabilities, and then pass these bounding boxes with images to segment anything model, and get the masks along with the text queries that I have queried. So you can basically, the best way of doing OpenSet image segmentation is through combining the OpenSet object detection models with mask generation models at this point. I think the state of the art was, so there's another model called grounding dyno. Combining grounding dyno with SAM, I think, was the state of the art. And moving on to the hot topic of today's vision language, today's multimodal area, I kind of wanted to pass these a bit fast because I just wanted to give some background information about zero-shot models before coming to the main topic of this talk. So vision language models are essentially language models that can take in image and text prompts, but also they can take in video as well sometimes, which I'm gonna come later on. But these models can understand the image. They can do, for instance, object localization, zero-shot segmentation, object detection, like zero-shot object detection, visual question answering, one-shot learning with instructions, and so on. So for instance, you can see here the input and the output of a given vision language model. And if you would like to learn more, we have written a very long blog post at hf.co/blog/VLMs. But today's talk should suffice. So how did this start? The reason why I wanted to give a bit of background on stuff like CLIP was because I wanted to have a primer on how the multimodal area kind of evolved through time. So for instance, one of the first successful experiments of having a vision language model was Lava. And Lava basically consists of three things. First one is an image encoder that was previously pre-trained in a dual encoder setup. Like for instance, you have CLIP. CLIP consists of an image encoder and text encoder. They basically get that image encoder because that was already made to understand in a way, like it was already aligned with a text encoder. And you have this projection layer, which in Lava's case is a multi it's a MLP, and then you have language model, like it can be any language model, like a large language model, small one. It's just a text decoder. So what they do is that they basically, so it consists of two stages. The setup of aligning a vision language model. So first one is you have this image encoder frozen. You do not change anything in this image encoder, and you do not change anything in the language model as well. You just unfreeze initialize the multimodal projector, this part, which is an MLP. And you pass these images and then also the text to text decoder, and just train this part to align this model to sort of project the features from the image encoder and also the text decoder. And then on the second stage of this alignment process, you would just unfreeze this part and fine tune it on a downstream task. It can be chat, for instance. It can be instruction. There are many data sets out there, but basically this is sort of like a pre-training, and this part is sort of like a fine-tuning phase. But this was just what happened with Lava, and for a while this continued. So basically what people do is people swap this image encoder with different image encoders like Siglip, different clip alternatives, and so on. And then with the text decoder, they try multiple things like Llama, um, QVAN, and other text decoders. So there is like three types of these VLMs. First one is the base models, which are basically going through pre-training part. Basically, like they just train the multi-model projector between these two components. And the second one is models that are fine-tuned on instruction. Again, they unfreeze this part, and this part just pass instructions. And the last one is the chat models, which is basically models fine-tuned on chat with this stage. So one of the most exciting models of this year was Polygemma. Polygemma is a model released by Google, and they have used the Siglip image encoder with the Gemma model. And basically they had linear projection. This says tokens, but it should be embeddings. Basically, they concatenate the projected image representation and text and then pass it to Gemma. And they have released three types of models. First one was basically pre-trained model of like pre-trained Polygemma. The second one was called Mix, which is basically models fine-tuned on a mix of tasks, such as OCR, model that can do OCR, model that can do the data set for captioning, like various things, not only single task. And then there is fine-tuned models, which is models fine-tuned on single task. And this model was revolutionary because it was the first model that could have done segmentation. But the way it does segmentation is a bit different, which I will come to later. Basically, it had something called codebook indices. Basically, it outputs segmentation tokens. It outputs object detection tokens here, as you can see, the ones that start with log. And it also outputs segmentation tokens. And they have trained the VAE to decode these segmentation tokens into masks, basically. So it segments like this. And having said this, I really discourage using vision language models for segmentation or object detection. The reason why is because, like, what makes these zero-shot models is actually the image encoder. Also for OWL, it's the text encoder as well. And OWL is a more task-specific model. Like both of them share the same, more or less the same components, but vision language models are actually more generic for many tasks. Meanwhile, zero-shot object detection models are more task-specific, thus they perform better. So I highly suggest not using. And also, like, if you can see here, it's not really decoding well. Like these masks aren't super precise to my observation. So I would definitely use something like Owl SAM or Grounding SAM just to be sure. So basically Polygemma is a bit of an old model, but I still wanted to show it because this model, this reason why this model was released is because this is a model that can just perform very well when you fine tune it. So this model is not a generic model for a lot of tasks. It's also a small model. It's like 3B, but it's a good backbone to be fine tuned on your own task. That's why I wanted to show it a bit. coming to today's models, first one is Q12 VL, which was quite revolutionary in the past few months. There's also Q1 2.5 VL, I think. This model just performs so well, and I think it's currently the state of the art, from what I remember, in the vision arena, which I'm going to show later. If you don't know, it's okay. But this model is a very generic vision language model. It comes in multiple sizes, including 72 billion parameters. There is one for 7B parameters. I think 72B wasn't open source, but it was open weights, and 7B should be completely open source. And it performs really well. It can handle dynamic input. It can take in interleaved image, text, video input. If you don't know what it means, it means that within the text you can talk about multiple images and point out to a specific image, and it consists of a vision transformer based text image encoder that they have trained. And I think it also has 2D rotary position embeddings as well, which is a change compared to the previous architectures. It has an MLP projector, and it consists of Q12 language model here. And it is multilingual as well. They have trained on many languages, and some checkpoints are Apache 2.0. The second one is Pixtral, which is another very good model, and I think it is Apache 2.0. It is 12 billion parameters, and it can also take in interleaved image text input, I think, and it consists of 12B Mistral Nemo decoder, and it can also handle variable image sizes. I think last one is Molmo. It was quite. It's a great model in my opinion. They released nearly everything openly. I think they also released the dataset. Basically, people are releasing the models openly most of the time, but they are not releasing the datasets openly because to my observation, what gives the competitive edge to many companies is the labeled data. I mean, it's quite costly to label the data, so it just makes sense. But also, most of the companies that actually release the models openly, they do not really release the datasets openly. So kudos to LNAI folks for releasing Molmo completely open, as well as the dataset. It is basically clip encoder with different decoders. The license depends on which language model that they are using, because like even if you want to release something openly, if any of the components that you are using is not released open source, you cannot do that. You have to stick by the license restrictions. So in this case, there is Molmo 7BO, which is basically the checkpoint that consists of almost 7B. I think there is one more, like another 7B checkpoint, which I don't remember as of now which one it was, but it was completely open as well. There is Molmo 72B, which is based on Qwen 72TB, and there is Molmoi, which uses Olmoi, which is a mixture of experts text decoder model. And the cool thing about this model is that it can also point out to things in the image and also do counting, which was something we didn't see with the previous models. Yeah. So how do they compare? Is a great question. So there is two things. First one is OpenVLM leaderboard. So this leaderboard, you can go with this link. evaluates every vision language model based on a set of benchmarks. These benchmarks vary from document understanding, mathematics solving. There is, for instance, Blink benchmark that assesses how a model responds to things that it sees in like a very short time, like we humans do. um, there is mixed benchmarks, there is OCR benchmarks, there is chart understanding, there is a bunch of benchmarks. And to be honest, like every model that is released uses certain set of benchmarks to evaluate their model. It can be due to how they use the training set of those benchmarks in their downstream fine-tuning parts, like the second stage. And that they do not want to evaluate their model on the tasks that their model hasn't seen. But this creates a bit of confusion because every single model, to my observation, again, this is not roasting, but every single model is just evaluating on different benchmarks, which creates a huge confusion because the numbers do not add up. They just put a certain set of benchmarks and then they put the average of it. But thanks to these type of leaderboards, which these leaderboards as well might not be including the benchmarks that those papers were evaluated on, but it has separate set of benchmarks. You can just compare these models well. But this is just an observation and take this with a grain of salt. For instance, there is intern VL2, which seems to be the best model on these set of benchmarks. There is MVLMD, which was released by NVIDIA a while ago. Um, it's not performing too bad, and there is more. So if you visit this link, you can also see the proprietary models, but I didn't include them in this, or like the models that can be accessed through API. You can filter them on model size as well, which is pretty good in my opinion. So how do they compare? There is another thing called Arena, which I think is better, in the sense that these benchmarks are sometimes too biased, or these benchmarks can, some of them are generated through some proprietary models. And because of that, if your prompt is not styled, like if your model's training data is not included, is not including the style of the prompt of, for instance, like Gemini Flash, or I don't know, GPT-4 V or whatever, your model might be performing bad on those prompts. This was something I read on a paper, which was super interesting. But in the end, I think Arena is what matters, because like this Arena, basically, if you don't know about the Arena, it is basically you have these models in the backend. They bring you, they sort of let you enter an image and the prompt, and then they send these to two models in the backend, and then they bring you the outputs of those two, like of those two models, without telling you which model has the which output. And then you can pick it it's basically based on human preference. You can just pick either one of the outputs. And then these are called battles. And you can see here the battles, number of battles, the arena ELO, and so on. And I'm quite happy about this, because a month and a half ago, in this arena, there was only three models that, like on the top 20, there was only three models in here. And the best model was, I think, QN, that was around 13 or something. It wasn't performing well, but now we have more models and they are ranking way better. So it's pretty exciting. There is QN, there is Pixtral. Someone asked me why these models have lower number of battles. The reason why is because these multimodal vision language models first appeared with the proprietary models like GPT-4 or Cloud. And now we can just distill the outputs of these models and train new models, have more data. And this is how new models are trained. And because they are submitted later on this arena, they have less number of battles. And this is the reason why we used to not have a lot of models in this part, but rather have now have, but still number of battles are quite low. And here you can see the open source models, and you can go with this link. It is maintained by LNAI. Again, head tip to the maintainers. So my favorite part of this talk is what has changed since the lava revolution. And I'm going to talk a bit about some recent trends. So basically, I read a lot of visual language model papers this year, and I wanted to compile the common trends that I saw in those papers. The first one is the fact that people are using multiple image encoders now. There is Mini Gemini, which you can see here. There's Mplug, the Cowl, and there's Brave. These three models are using multiple image encoders to train better models. From what I understand, so basically one model, one image encoder is CNN based, and the other one is vision transformer based, and one has better resolution, and this way, like, you have this high resolution features, low resolution features, and then they concatenate. Most of the time they concatenate the outputs and just pass it to the projection layer, and later pass it to the um, text decoder. In this case, Mini Gemini is a pretty cool paper because it sort of generates this prompt. Um, like it gives you some output text, but it also generates a prompt which you can pass to a stable diffusion extra large and generate an image. This is quite extra, but this model basically takes image and text input and outputs image and text output if you plug in the SDXL parts. Brave model was pretty cool as well. Basically, it's a paper by Google. They create this. I don't know if I added it. No, I didn't. So basically, they create this system where they can add as much image encoder as they can, and then they pass the outputs to a module called MEQ former to reduce the outputs, like select the best representations and concatenate and pass to the text decoder. And this performs better than models that have a single image encoder. And then you can just scale it so much. And the cool thing is that with this model, you only train the projector. From what I remember, you do not change any image encoder. So the number of trainable parameters was also low. You can train the MEQ former, yes, MEQ former, and the number of trainable parameters is quite low, so it's quite scalable and nice. And MPlug.call is another cool model, which has two image encoders from what I remember in serial. Like this here, they are parallel, but I think that model had like a serial setup. And then there was a separate module called H reducer, and then it was passing the output. And it was the best document understanding vision language models at some points, but not anymore. I will explain why. Another advancement is being able to have interleaved inputs, in the sense that you can refer, for instance, in here, you can refer to the images through the text, so that you can just make references. And for instance, like you have in here, you have multiple images of a fork's position, and then it can be used for stuff like embodied agents. Like for instance, in here, place a glass with a fork in it on the table in front of a glass pitcher and step details. You can just insert the image inside the text. And this, I think it came with IDFX at first. I don't really remember which paper did it first, but IDFX is a paper released by Hugging Face, a model released by Hugging Face. And it had interleaved image and text. And then there is models that can take in interleaved image, video, and text. What you do is you have, I think this model was doing it. Basically, you have the video, and then you downsample the video, like take every X frames, like one frame every X frames, and then pass it as to the model. You either insert as many image tokens as you downsample. So assume you downsampled 8 frames, you insert, like in here, 8 image tokens, or you can insert a single video token depending on the model that you are using. But you can just interleave image, video, and text, which is pretty cool in my opinion. And another cool one is not about interleaving, but this model excites me very well, and it was just released yesterday or the day before, I think. It's called Longvu. It was released by Meta, and they input downsample videos, but they downsample the videos pretty smartly. I don't know if I add it here. Yes. So basically, they basically have this. So there's a model called Dino, which is an image feature extractor. They downsample the frames by passing the frames to Dino model, which gets rid of the redundant frames and based on similarity. And then they have another module based on Siglip and Dino, which assesses whether the text prompt is like the frames that matter to most to the text prompt. So it's sort of like a cross-modality, cross-model importance. And then they pass the final reduced frames to the large language model. And this is the state of the art as of now. This is pretty smart because normally we used to just brute force downsample frames and just pass to the language model. And last two of them, I think, is having different pre-training and post-training setups. So with Lava, we would just pre-train the multimodal projector and then fine-tune by unfreezing multimodal projector and text decoder. But this time it is a bit different. Like this paper called General OCR Theory basically does something else. It initially trains a whole network based on a vision encoder, MLP, and and the OPT, which is like a very old model by Meta, a text decoder. And then they just strap this vision encoder and then align it with QN 0.5B. And then when they are doing downstream fine tuning, they freeze this vision encoder, which is super interesting in my opinion. Normally, what you would do with the, like when you, like the reason why you would unfreeze an image encoder and train it is because you need a domain shift. So you have this clip model, for instance, and if you need something to understand some, I don't know, MRIs or whatever, you need to unfreeze that model to do the domain shift. But in this case, you are not. You are completely training stuff from scratch. And this model performs super well. You have to see it. It's just so good. And as I mentioned before, these models can do zero-shot vision tasks. It started with Cosmos 2 model by Microsoft. It was able to do reference from the image to bounding boxes. And then there was Polygemma, which could do segmentation on top of object detection. And now we have Molmo, which can do counting and pointing out to things. So lastly, there is VLMs for retrieval, which can be used for multimodal RAG. The most famous one is called Poly, which is basically you have Polygemma, and then you have normal Gemma or any language model, and then you take the projected outputs of this model and this model, basically two embeddings when you think about it. And then you have a module called Maxim that calculates the similarity score between these projection layers to maximize the image to text. And this is better for multimodal RAG setups because you have these documents and then you have a text query. What you would normally do is you pass these images through a PDF parser that includes an image captioner, OCR, I don't know, table to markdown, and then make it into a complete text, and then just pass this document to a retrieval model, text retrieval model, and then pass this to an LLM to do RAG. But this setup instead, where you have documents and you have text query and you pass it to call Poly, this, and take the best matching documents and passing it to a vision language model, sort of like a visual question answering, and getting the augmented answer is way better. It is less brittle, it works better. There is now lightweight models like DSC, which can do it very fast, and you can shrink it with less performance degradation as well. So coming to the last part of my talk, I know it's a bit fast, but I wanted to tell as much as I could with this talk, like sort of like a compressed ecosystem. So coming to the tools, you can just like if you assume you have a workflow in which you can just find a model, you can customize this model according to your use case and then deploy. We have a set of tools for doing this workflow completely open source. So first part is Hugging Face Hub. You can just go to Hugging Face Hub and take a vision language model, or you can go to the OpenVLM leaderboard or Vision Arena and take a model to be fine-tuned. So for instance, Polygemma is a pretty popular one. And ever since we have released the fine-tuning script, there has been so many people training adapters or directly fine-tuning the full model. And yeah, you can just find an open source model to do this. Um, if you find an instruct model like this, like QN 2.5 VL instruct, you can also directly use that for your task. But if you need fine tuning, I have a bunch of fine tuning scripts. I'm going to give the link at the end. And after you fine tune the model, which I'm going to show you how to do so, but after you fine tune the model, or like if you have directly find the model that you want to fine tune, you can deploy it using these three libraries. So VLLM, Llama CPP, and text generation inference. I'm a bit biased because I work at Hugging Face, so I put the script for text generation inference. But all of these are more or less doing the same thing. Like they have features like tensor parallelism, which if you cannot fit in your model, they have token streaming, they support quantization, they have flash attention, they have more or less the same features for serving a given model. And this, for instance, like for to serve a model, like in this case, I put an LLM, but you can also put VLM. It supports Polygemma, I think QN, I'm not sure, IDFX, Lava models. It's like one line of code to start serving a model in a very optimized manner, because these have like text generation inference has like specified CUDA kernels to serve models more efficiently for you. So it's basically just very convenient. But these two libraries, packages, toolkits are also the same. I'm coming to an end of my talk, by the way. I'm going to wrap up very soon. I'm very sorry for taking it a bit of time. Another library is, I mean, Transformers is quite popular, I think, right now. It is a library for fine-tuning, doing inference on transformer models. It doesn't only have transformer models, but the most popular ones are transformers. And it has some auto classes. I will not go through a lot, but these are essentially for loading models and loading their processors. And yeah, I'm not going to go through the API quite a lot. Bits and Bytes is a library for 8-bit quantization of these models. Basically, how you would load a Hugging Face transformer model, you can just add few lines of code, like even like one line of code, and it will load the quantized weights. There is parameter efficient fine tuning, which is another abstraction around transformers with adapter models, like techniques like low rank adaptation, like LoRa, Dora. You can also do quantized LoRa, which is you load the model in quantized way and then do LoRa fine tuning. And if you have, so lastly, there is TRL, which supports reward optimization techniques like alignment techniques for large language models, vision language models, and it supports parameter efficient fine tuning, bits and bytes to do LoRa. And if you want to learn more about them, you can go to my repository, and you can also read our blogs about vision language models. Thank you. I know I'm a bit of I ran out of time. I hope it was useful.